So here actually in the first problem we find out the angular momentum of this rod. So this rod actually rotates about this y-axis with an angular speed of omega, and the rod rotates in such a way that the axis of the rod remains on this cone or on the surface of this cone. So the rod rotates like this. Now you have to find out the angular momentum of the rod with respect to xyz axis for the particular position shown, and it's looks simple. So what you can do is so the rod is rotating about the fixed point O. So what we can do is we HOX, HOY and HOZ is equal to the I matrix, which should consist of IXX, IYY, IZZ and the product of inertia terms multiplied by omega x, omega y and omega z. Now here the problem is how to find out this I about O with respect to this small x, small y, small z coordinate system, because it is difficult to get the moment of inertia of this rod about this small x, small y, small z. But it is very easy to get the moment of inertia about an axis aligned with the rod. So if we take this axis y dashed z dashed or x dashed y dashed z dashed, and just we rotate this y and z about this x axis. So x dashed is in the same position as x and y goes here to y dashed and z goes here to z dashed. So it's very easy to find out the moment of inertia of this rod about this x dashed, y dashed, z dashed, because since it is a thin rod, the moment of inertia I y dashed will be 0 and I x dashed will be 1/3 m l square, and I z dashed will be also 1/3 m l square, and the product of inertias would be zeros. So this should be I dashed about O, that is I xx 1/3 m l square, I zz 1/3 m l square and I yy 0, and all the product terms are 0 because this is the symmetry axis. So IYY is 0 because the rod is very thin. So now what happens? Now we want to get, once we get the moment of inertia values with respect to x dashed, y dashed, z dashed, we want to get the moment of inertia values about x, y, z, and for that we have to make the transformation. So x, y, z is final and x dashed, y dashed, z dashed is initial. So we want to go from here to here. So the transformation matrix should, this final x should be first. So this is cos of x, x dashed, cos of this x first, x, y dashed, and cos of x, z dashed. Similarly y comes first, y x dashed, y dashed, y z dashed. Now what is x dashed? X dashed is 0. X dashed is 0 and y dash is 90 degree and x z dash is also 90 degree. So this is 1 0 0. Similarly this should be also 0 0. So this is 1 0 0 and this is again 1 0 0. And here cos of y and y dash. What is the angle between y and y dash? It is theta. So this is cos theta. And this is y and z dash. So what is the angle between y and z dash? That is 90 degree plus theta. So it should be minus sin theta. And what is the angle between z and y dash? The angle between z and y dash is 90 minus theta. This angle z and y dash is 90 minus theta. So cos of this is sin theta. So here sin theta, and again cos of z and z dash is again theta. So this is cos theta. So we have got the transformation matrix. Now we can get I using this transformation matrix, and you know this relation. So now if you multiply, then you get this as your I. So this is I xx, this is I yy, this is I yz, this is I zy, and this is I zz. Now hx, hy, hz will be this, because omega is about y axis. So omega x is 0, omega y is omega, and omega z is 0. So you just multiply and get hx, hy, and hz, and you get this result. So in this example, this is an aircraft landing gear viewed from the front. That means the aircraft is coming towards us, and the aircraft landing gear viewed from the front is being retracted. So it is retracted in this direction. It is retracted in this direction, and immediately after takeoff, and the wheel is spinning at the rate corresponding to the takeoff speed of 200 km per hour. So this instant shown is just after takeoff, and the wheel speed and the wheel spin speed corresponds to this 200 km per hour takeoff speed. The 45 kg wheel has a radius of gyration about its z-axis of 370 mm. That means about this z-axis, the radius of gyration is 370 mm. Neglect the thickness of the wheel. The wheel thickness can be neglected. That means the wheel can be taken as a thin disc. And calculate the angular momentum of the wheel about g, that is about the center of mass, and about point A for the position where theta is increasing at the rate of 30 degree per second. So see here, this is this x, y, z is actually fixed to this part, and the wheel is fixed to OA. This x, y, z is actually fixed to OA, and this wheel is spinning about z. So this, just observe that this x, y is coming towards us, x, y, z is fixed to this OA, and the wheel is also spinning about this z. So the angular velocity of the wheel is the speed of retraction of OA plus the angular speed of the wheel. And what is the speed of retraction? That is theta dot in the negative y direction. So minus theta dot j, and phi dot, since the aircraft is coming towards us, then this wheel must be rotating like this from here to here. So wheel must be rotating like this. So the spin speed of the wheel is in the negative z direction. So minus phi dot k. So this is the angular velocity of the wheel. So now this phi dot, as you know, corresponds to 200 km/h. So the speed is 200 into 1000 by 3600 meter per second, and phi dot is this v by r. So this divided by the radius of the wheel, which is 0.920 by 2. So this is the spin speed of the wheel. So we have got the spin speed, and theta dot is already given, which is 30 degree per second. Yes, it is 30 degree per second. So it is 30 into pi by 180 radian per second. So now we get omega. Now what is the angular momentum of this about xyz? That is I omega. So I matrix into omega, and Ig, that is the angular momentum with respect to, Ig is the moment of inertia with respect to x, y, z. That means this is Ixx about center of mass, about g, this is Ixy like this, and this is Iyy. So due to symmetry, so we are taking about Ixyz, and due to symmetry the product of inertia terms are 0, and Izz is mass into radius of gyration square. So Izz is, this is Izz, is mass into radius of gyration square, and since it is a thin disk, Ixx and Iyy, that is the diametral moment of inertias, are half of Izz, since it is a thin disk. So Hg is equal to Hg is Ig y omega y. So here omega is having one y component and one z component. So Hg is omega x is 0, so this multiplied by 0, this multiplied by omega y, and this multiplied by omega z. So this also includes the minus sign. So this is omega z. So now Hg is this, and it is easy to show that Hg is this. So next they ask, what is the angular momentum about A? So about any point, we know the angular momentum about G is I matrix into omega vector. Similarly, angular momentum about a fixed point is moment of inertia matrix about that fixed point multiplied by the omega vector. By multiplication we mean matrix vector multiplication. But what about a point A which is neither a fixed point nor the center of mass? So the rule is, about any point P, the angular momentum about any point P is the angular momentum about center of mass plus a vector from P to G. That means that point about which we are interested to calculate the angular momentum to the center of mass, multiplied by the total mass and the velocity of the center of mass. So here we know Hg we have just now calculated. Pg, in place of Pg we will get Ag, in place of Pg we will get Ag, because we have to calculate angular momentum about A, and this m is the mass. And what is the velocity? What is the velocity of G? Because we have to find out what is this Vg. So what is this Vg? Vg is the velocity of the center of mass. The velocity of the center of mass is velocity of the center of mass is, see, this center of mass is actually fixed to this OA. So this G point is fixed to this OA. So the velocity of this point is omega cross O to G, where omega is the omega of OA. That means minus theta dot J, that is omega cross OG, will give you the velocity of G. So this is OG cross minus theta dot J. So what is OG? OG is OA plus AG. OG is OA in the OA plus AG. OA means in the x direction OA, then AG in the z direction, and AG is given as 0.215, but OA is not given. So OA is not given, so we are keeping it as OG as 0.215 K plus OA along I. Cross this. Now this actually is not required, because when you take this cross product, so K cross J is minus I and I cross J is K. So this K, when again if you take cross multiplication of this with K, so this goes off. So whether the value of this is given or not given, it doesn't matter. So here you get, so if you compute this, then you get Hg minus 1.09 J. So Hg is already known. So Hg is already known. This is Hg. So this is this minus 1.09 J. So this is the value of Hg you get. This is the value of Hg you get.